Today we are delighted to have a special guest on your channel. His name is Mr. Surya Asthana. He has currently finished his doctoral research work in the topic of quantum communication, and to be specific, in interrelation of non-classicality features and application to quantum communication. So let me give a short introduction about Mr. Surya Asthana. He did his BSc in physics from Kanpur University, and he was a gold medalist in MSc in physics from IIT Delhi. And during his PhD, he has published 10 highly reputed journal papers and 5 international conference papers. And he also wrote single author paper during his PhD independently in the field of quantum communication. So welcome, sir. Welcome to the channel.
Yeah, thank you, Sathi, for having me here.
So today, sir is here to teach most of the YouTube students about the basics of quantum mechanics. In earlier videos, he has shared valuable information and suggestions on the research field in quantum mechanics, on the research in the field of quantum information theory, and also he has shared many different interview preparation tips and how to prepare so that your interview will be good and you will get selection in IITs and other research institutes. So today he has kindly find some time to give in our channel to teach you the basics of quantum mechanics. So sir, please continue.
Okay, so let us start today. The plan is that we will start with the basics of quantum mechanics and in particular universal features of Schrodinger equation for bound state systems. Okay, so today's focus will be on bound state systems, and secondly, the point is that we will not go into that much calculation part. Our focus will be, because in most of the interviews or most of the questions in competitive exam, we do not have that much luxury of time. So we have to have some intuition. So we will try to see, without doing brute force calculation, what we can infer about different problems in quantum mechanics with regard to Schrodinger equation. So let us start. So I will share my screen. Yeah. So just a minute. Is my screen visible?
Yes.
Okay. So now let us try to. Yeah. So today's focus is on, in particular, Schrodinger equation. And bound states. So Sathi, please let me know when I have to conclude. Okay, so the point is that Sathi, am I audible now?
Yes, sir, you are audible.
Okay, okay. So the point is that this is the Schrodinger equation. H sign is equal to E sign. So this is your H. So when we say that this is Schrodinger equation, this thing is not completely correct. Okay, because the actual Schrodinger equation is this thing: IH bar del sine over del t is equal to H sine. This is the actual Schrodinger equation, which is time dependent. And one thing which I want, so time dependent Schrodinger equation, which I want all of you to focus on, is that it is first order in time. So first order in t. And secondly, there is a Hamiltonian. So it is assumed that the system which we are dealing with allows for Hamiltonian. Okay. So what is this thing? This is T plus V, where T is what? T is your kinetic energy. and V is what? V is your potential energy. So the point is that when we try to write, we will write T plus V sine. And in general, this sine is a function of space and time both. There is no a priori reason for this sine to be a function of solely r coordinate. Okay, so this is the thing. Now this T for all the systems, this is like P square over 2m, and this V, this changes from system to system. So the point is that suppose somebody asks, okay, so where is the physics of the system? How is the physics of the system governed? So it is the potential that governs the physics of the system. Okay, whether it is a free particle, it is a particle in a box, it is a simple harmonic oscillator, it is a finite square well potential, so on and so forth. So it is the V that changes from system to system. That is point number one. Point number two, that this thing, suppose, so far we have not made any assumption. Now comes a very important assumption. What is the assumption? That V potential which we are writing, V of r comma t is identically equal to V of r, meaning this potential is a function of space only. It is not a function of time. Now, under this assumption, what happens? When we go to the previous slide, what we have written, T plus V sine r comma t is equal to this. So now we will substitute this thing here. So T plus V sine r comma t is equal to I h bar del sine r comma t over t. Now, all of you are familiar from your differential equation thing that if there are two sides, now here there is a solely a derivative of t. Okay, and here it is a sole function of x or r. There is no t. So what? So under this assumption, we can make use of what is called as separation of variable. Okay, and when we do the separation of variables, so I am not getting into all these things today. If you have some problem, you let us know and then we will do that thing. So the point is that when we do the separation of variable, then what we end up with is this equation, that minus h bar square over 2m del square plus v r, okay, sine r is equal to e sine r. Now this is your time independent Schrodinger equation. Now, while going from time dependent to time independent Schrodinger equation, we have made use of the fact that our potential is not time dependent. Okay, and then we have made use of separation of variables, which I have not shown you explicitly, but I am telling you in words. And this E is your energy. So if this is the equation that governs, so then what conclusion can we draw without solving this equation explicitly? So let us study this equation. So minus h bar square over 2m del square plus v sine of r is equal to E sine of r. Now this is in position representation. As all of you might know, that this is your kinetic energy operator in position representation. You can also write it in momentum representation, and then it will look like this. So here we are comfortable in writing. Now suppose I will give you an example. So here there is another problem statement. Suppose Hamiltonian H. Okay. Suppose this Hamiltonian H commutes with some operator, some transformation T. Okay. So H comma T, actually I should make it some curly T so that we do not get confused with kinetic energy. So suppose there is some transformation curly T, so Hamiltonian commutes with it, and I should explicitly write this is some transformation. And this is not without its merit. I will tell you what it is. Okay. So Hamiltonian commutes with some transformation. So what is the suppose we are given this information, what extra can we get? Okay, so let us look at this thing. Our equation is H psi r is equal to E psi r. Now what we have been given, H commutes with T, so Ht is equal to 0, and T is a transformation, so Ht minus Th, this is equal to 0. In other words, Ht is equal to Th. Now, since T is a transformation, so what we can do, we can also write it like T inverse Ht is equal to H, because every transformation can be undone. It is like you rotate something, so you can rotate it back. Okay, so this is the thing. So now the point is that we combine these two equations. So instead of this H, what we will write? We will write T inverse Ht sine is equal to E sine. I hope everyone is convinced with it. We have not done anything great. We have started with the time independent Schrodinger equation. We have made use of an input. So this is an extra input. And I will tell you explicitly in a minute where this extra input comes from and where we can find the example of this extra input. Okay, so the extra input is that H commutes with the transformation. So if my H commutes with the transformation, then I can make this thing look like this, that Ht minus Th is equal to 0, Ht is equal to Th. And since every transformation can be undone, so T inverse exists. And I am multiplying this equation by T inverse here. So T inverse Ht is equal to T inverse. So I should write it. So this implies T inverse Ht is equal to what? T inverse T into H, which is nothing but H. So here this equation comes. Now I am combining these two equations. So T inverse Ht sine is equal to E sine. Now we will go to the next slide and we will see what it is. So T inverse Ht sine is equal to E sine. Now again we will multiply on the left by T, so both sides. So T inverse Ht sine is equal to, because E is a number, so T is an operator, so T sine that will go this way, and T inverse T, that is identity. So what we get, Ht sine is equal to Et sine. So I would like to draw your attention to this equation. What we have started with, this equation, H sine is equal to E sine. We have made use of this input, and together with that input, what we have landed up with this equation. So now we have this thing, that we have equation with which we have started, H sine is equal to E sine, and then we have this thing, Ht sine is equal to Et sine. That means that T sine, what is the meaning of T sine? Is an eigenstate of the Hamiltonian, is an eigenstate of H belonging to the eigenvalue E. And here what we get, psi is an eigenstate of H belonging to the eigenvalue E. Okay, now comes an extra assumption that if my Hamiltonian, if H has non-degenerate spectrum. So if H has non-degenerate spectra, meaning corresponding to a single eigenvalue corresponds to single eigenstate. There is no degeneracy. Okay. So what it means that my T sign is proportional to sign, because my psi can differ from an overall phase. So T psi can at max be e to the power I theta sine. So the point is what this thing is telling you. This thing is telling you that if my Hamiltonian has a particular symmetry, this is the input now with which we have started. So if my Hamiltonian has a particular symmetry, then my eigenstate also has that particular symmetry. Meaning the eigenstate remains unchanged under the action of that symmetry operation. My T psi is leaving the state invariant, is at max changing the state up to an overall phase. Okay, so let me summarize this thing and then I will go to example and then you will better appreciate what we have discussed so far. Summary is, if H commutes with T and H has non-degenerate spectra, then the eigenstates of H are invariant, are left invariant by T. That is the step that we are making. Now let us see in some examples. So there are certain examples. And what is the example that we will take? We will take our first example as particle in a box. So this is our potential. So as you people might know that whenever we have a problem in quantum mechanics, it is characterized by the profile of the potential. So when we are saying that particle in a box, we have to first give the profile of the potential. So this is our profile. So I should change the color for a better visual look. So minus A to A. This is my X. This is my V. Okay. And here it is infinity. So the point is that the particle is bound from here to here. So when we will write it, how we will write? V of X is equal to 0, X minus A to A, and infinity otherwise. Now you see that if we change X to minus X, so our transformation is X to minus X, my V of minus X remains unchanged because this thing is unchanged. So it is said, if you look at some book in quantum mechanics, they say that the potential is parity symmetry. Now, I hope that all of you are aware of the fact that this X going to minus X, this operation is called parity operation. Okay. So the point which I am trying to draw your attention to, that my potential profile is parity symmetry. So V of X is equal to V of X is equal to V of minus X. Now let us look at eigenstates. So we assume that we have solved with the Schrodinger equation with brute force, and eigenstates come out to be, if you solve for this thing, you can give it a try, cos n pi x over 2a. Now this, if you make this change, x goes to minus x, and this is sine of x. So sine of minus x, you can see that it is equal to sine of. So if my potential is parity symmetric, my wave function is also parity symmetric. Getting my point? That this is the symmetry of potential. But one thing I have very cleverly skipped. So I should draw your attention to that thing as well, because we have said that it is the symmetry of the Hamiltonian, not just the symmetry of the potential. So my H sign, let us look at the form of H. H is like T plus V. Now T is like P square over 2m. And this involves a derivative, minus H bar square del square. So this is always parity symmetry. Parity symmetric always. And this V, in this case, it is not always mandatory that it should be parity symmetric quantity. But in this example that we have considered, particle in a box, for this particular thing, V is parity symmetric. And thanks to this thing, what we have been able to infer or explicitly see that sine of minus x is equal to sine of x. So what is the significance of this result? Suppose I give you very bigger potential. So my potential is not smooth. It has a lot many wiggles like this thing. This is my potential profile. But what I tell you, so this is like my V of x, and this is like my x. But one guarantee I give you, that there is a promise that V of x is equal to V of minus x. That is why I was a bit cautious in drawing this thing. So I have drawn it by hand. So, but what I have tried to tell you is that V of x is equal to V of minus x. Okay. So if that is the case, then suppose I say that there are 4 possible solutions: first, second, third, fourth, and then in these 4 solutions, this is sine of x is equal to sine of minus x is equal to sine of x. Here sine of minus x is not equal to sine of x. Here also sine of minus x is not equal to sine of x. I give you some form. Let's say sine 1, sine 2, sine 3, sine 4. And for sine 4, you also check. So then if I ask you which is the valid or which qualifies to be a legitimate solution, so your answer without solving the equation is that sine 1. Because if this is parity symmetric, your wave function also should respect that symmetry. So this is our lesson number 1. That if there is a symmetry in the Hamiltonian, my wave function also has that particular symmetry, provided my eigenvalues are non-degenerate. Let us look at another example, which is very, very important and which we study quite a lot. Example 2, simple harmonic oscillator. Simple harmonic oscillator. So my H in this case looks like this. So you can see that if we change x, h of x, if we write it like h of x, so if we change it to h of minus x, so you can verify that h of minus x is equal to h of x, and that this is the reason that all the eigenstates, they have definite parity, meaning either they have even parity or they have odd parity, meaning either sine of x is equal to sine of minus x is equal to sine of x, this is called even parity, or sine of minus x is equal to minus sine of x, this is called odd parity. Okay. So that is the thing. So this is another example. So much so for our this one symmetry principles. So this is a very strong principle and it works. These two examples are just for convincing you it works, or you can use it in an interview or in an exam when you cannot solve the equation by brute force method. Okay. Now comes another important feature which is called as scales. So again we restrict ourselves to bound state systems. Okay. So the point is that it is a peculiar feature of quantum mechanics that it gives you a scale in every problem. So again, there is this. What is the use of this feature? The use of this feature is that suppose you are asked to solve a particular problem. I will tell you what kind of problem. And then you have been asked to calculate a particular quantity. So there are four options given to you. You can reject some of the options. You can strike off some of the options from using this dimensional analysis. So we will again give example of a particle in a box. So particle in a box. So you see that there is a length scale which is given to you, L. So suppose someone asks you calculate the mean value of x. So whatever be the prefactor, it should come like A into L. Calculate the standard deviation, whatever be the prefactor. This A and B you have to determine, but L you are sure of because your scale of the problem has a physical scale and that is given to you by the length of the box. Okay. So that is one thing. Now again, and h bar is a signature that we have in Schrodinger equation. It is Planck's constant. So there is a scale for momentum. So this is your scale for momentum. So suppose you have been asked that calculate the average value of P. You don't know what you will get, but you are sure of that you will get in the units of h bar over L. You are sure of that you will get in the units of h bar over L this delta. Okay. So this is called dimensional analysis. I should convince you. Now let us look at energy. Now you see, you all of us are very meaning we memorize that the energy is n square pi square h bar square over 2 ml square. Now you see, suppose we don't know this formula. We pretend that we don't know this formula. How far can we go? So we have been given that the scale for x is L, scale for P is h bar over L that we have seen in the previous slide. Now what is the scale for energy? So energy is your P square over 2m. So you see 1 over 2m and P square is h bar square over L square. So h bar square over 2ml square, you see this far we are able to go and we have to fix only this factor which I am sort of. So n square pi square is what we have to fix by brute force calculation. Okay. So this we have to fix by brute force calculation. Otherwise, this far we are able to go solely by dimensional analysis. We have to invoke nothing other than dimensional analysis. Okay. So after this, let us go to another very important example, and that is your simple harmonic oscillator. So in the simple harmonic oscillator, so what I am requesting you to do, suppose you have been given a new problem, you are facing an interview committee and you have been given a new problem. So first of all, you should ask yourself, okay, what are the skills involved in the problem? So in a simple harmonic oscillator, let us, and in order to identify what are the skills involved in the problem, you should look at the Hamiltonian very closely and very carefully. So let us look at the Hamiltonian for simple harmonic oscillator. It is P square over 2m plus half m omega square x square. Now you see that how many quantities are involved? You have been given a mass, okay, mass of the particle. You have been given a frequency omega, which is fixed, okay. So these two are the things which have been given, and again h bar is always there. So with these three things, what is the dimension of energy that we can get? So dimension of energy, dimension of length, dimension of momentum. Okay. So the point is that we have, and dimension of mass is your m. Okay. So the point is that energy is what? Energy is always, we know that it is your angular momentum into frequency. So angular momentum is h bar and frequency is omega. So E, the unit of E is h bar omega. Okay. So the next thing is, what is my x? So for x, we know that half m omega square x square is my energy, which is h bar omega. This half is not of great concern for us because it is just a number. We are interested in fixing the dimensions. So x, the dimension of x is x square is rather h bar over m omega. So the dimension of x is square root h bar over m omega. This you already know. But the point which I am trying to stress upon, I will give you some questions at the end of this thing, which you can try and we can discuss in another video. And similarly, for momentum, so p square over 2m is also like h bar omega. So from this thing, p goes as mh bar omega. Now the point which I am trying to stress upon you is that suppose you have been given, instead of this 1 over this harmonic oscillator potential, which we all are very familiar with, suppose we have been given a new potential. Let us say we have been asked to solve for this potential, which goes as, or I should not write m, which goes as x to power 4. So half k x to power 4. This is my potential. Now in this thing, find out the unit of energy, the unit of x, the unit of p. What will they be? Okay. So this is, so these are all reverse problems. See, when we go in a competitive exam, it is very seldom we have been asked direct problems. But suppose we have been given some new problems, so how can we attack that thing? So we have not done any explicit calculation. When I say we have not done any explicit calculation, by that I mean that we have not tried to solve Schrodinger equation per se. But after that, what we have tried to gain is that without solving Schrodinger equation, we can fix the scales, we can reject some of the solutions. And after this thing, there is one last thing which I will cover in 5 to 10 minutes, and then we shall close. So the next thing is, what qualifies to be a valid wave function? So suppose, so let us start with a question. Suppose we have a confining potential. What do we mean by confining potential? That my particle is in a bound state. It is like harmonic oscillator, not necessarily harmonic oscillator. The input that has been given to you is that it is in some kind of a confining potential. It does not let the particle go away. So then if we are in a confining potential, this is the input. So suppose a particle is in a confining potential, and I say that this is one solution, wave function, this is another solution, This is yet another solution. And this is yet another solution. So which of them are valid wave function for a particle in a confining potential? Now, you look at the blend of opacity in this question, that we are not specifying for you what kind of a confining potential is. Is it like half x square potential, harmonic oscillator potential, or x to power 4 potential, or x to power 100 potential, or particle in a box, or particle in a finite square? Well, we are saying nothing about that. We are just saying that it is a confining potential. And if that is the case, then can we rule out something? Now you see that since we are, now here is the argument, the most important argument. So I want you to hear very, very carefully. So the argument is that if we are in a confining potential, then my x cannot have an arbitrary expectation value. The expectation value of x has to be a bounded quantity, and for that matter, every power of x should have a bounded expectation value. Why am I saying this thing? Suppose my particle is bounded. So bounded means no matter how high these points are, but the point is that there will be some, this one, that it can, there will be some classical turning points. Okay, so there will be some x min and there will be some x max, though this potential may not be roughly in the form of a parabola, it may have any form. This is just I have drawn it just for a schematic purpose. You don't take it very seriously because we have not yet specified the form of p of x. But what we are trying to say is that x min and x max exist. So your average of x, if you find out, so that will be between x min to x max. Okay, and all these, suppose you take x to the power n, they will not diverge. This is the most important criteria, because all the moments will be well defined. Okay, all the moments, because my whatever my p of x is, probability distribution that is given by mod psi x square, that will have meaning most of that thing will lie within this region. And suppose I try to draw my psi of x or p of x, so most of them, so let us say we will draw here, so most of it will lie in this region, and here there will be an asymptotic downward trend. So all those things will not diverge. Now let us see. Now this is the case. Now if we try to evaluate these integrals, so suppose we have a x square over capital X square, and we try to evaluate x to the power n from minus infinity to infinity. So you can see by explicit calculation that as soon as you have this thing, so if n is equal to 2 or greater than 2, so x square by x square plus capital X square, this roughly goes as 1. Suppose we neglect this thing, because this capital X, how high it is, how much high it is, the point is that you are going up to infinity. So the point is that it will be of the order 1, and when you integrate, you will get infinity, meaning it is diverging. This integral will diverge if you put n is equal to 2 or higher than 2. So this is not a valid candidate. In a similar manner, you can see that this is not a valid candidate. Only this and this, these two are valid candidates for confining potential. And yes, indeed, we see this kind of a downfall in harmonic oscillator and this kind of a downfall in hydrogen atom. So now we are sort of concluding. I leave you with one question with which we will start in the next video. Can you think? So the question is this, that Suppose you are not allowed to solve by brute force method, but can you argue that for hydrogen atom, purely from this thing, the profile of the potential for hydrogen atom, you will have this kind of a wave function, and for simple harmonic oscillator, you will have this kind of a wave function. Meaning, why is it that in hydrogen atom, the downfall is only proportional to x, meaning e to the power minus x, and here it is much more rapid downfall, e to the power minus x square. So I invite you to write your responses in the comment box, and then we will start in the next video from here. Okay.
Thank you so much for the very useful video and from the basics of quantum mechanics. And I have seen a lot of the classes, I have spent my MSc in BHU, so there are many professors who take quantum mechanics classes. And after that in PhD also from IIT Delhi. So, but your style of teaching is very unique and I really like it. Concepts are, it's like properly blended with different materials, like from the potential point of view, from the wave function point of view, and also with good tricks to solve those problems which actually candidates face in NET exam or GATE exam.
Okay. Yeah. Thank you for this. Today we have tried to keep it not mathematically that rigorous. We have especially tried to avoid solving the Schrodinger equation, and just by looking at the equation and the profile of the potential, how far we can. That is the basic aim of this lecture.
Yes. Okay, friends, please answer to this question that Shuryan sir has asked in the last. And also, I would like to inform you that we are conducting test series programs for CSIR NET Physical Science, June 2024. Please join those programs. The cost of the test series are kept minimal for the benefit of all the students. And the cost is because we will also discuss on the topics with individual platforms, and we will also check your doubts and your performance. So, but with a minimal cost offered compared to other institutes. And also we are offering interview guidance program that will provide you proper guidance to uh, give more understanding in the basics of physics. And we would always have Mr. Surya Asthana for more interview videos and also on the basics of quantum mechanics. So thank you so much. Thank you so much once again for your valuable time. And in the next video, we will also discuss the theory of quantum mechanics, and we will also have some revision of today's class. So please watch this video and share to all the needy students and subscribe to our channel for maximum reach. Thank you.